into going over PyLith, and then we'll do an example that runs all the way from the meshing associated with CUBIT or Trelis, running in a simulation with Paraview and visualizing the results, running the simulation with PyLith and then visualizing the results with Paraview. So we'll start off with what types of problems is PyLith good for, and some just sort of general conceptual examples. So we have quasi-static modeling associated with earthquakes. Some of the scientific questions that are in this area are: what is the stressing rate on some faults? Where is strain accumulated in the crust? What was the slip distribution in earthquake A? So doing an inversion, generally using static Green's functions, and that's something that Charles will cover in this afternoon sessions. How did some earthquake change the stresses on the surrounding faults? Post-seismic relaxation of the crust, such as what rheology is consistent with observed post-seismic deformation, and can aseismic creep or after slip explain observed deformation? PyLith also spans the region of dynamic modeling. Primarily, this is focused on modeling strong ground motions for forecasting the amplitude and spatial variation in the ground motion for scenario earthquakes or past earthquakes. Also, co-seismic stress changes and fault slip. Again, how did earthquake A change the stresses on the faults? And in this case, we may be wanting to look at the dynamic stress changes as well as the static stress changes. PyLith, on the dynamic side, also handles earthquake rupture behavior. There are a number of fault constitutive models available, and so someone may see observed rupture behavior in an earthquake and wants to understand the physics that were necessary or involved in creating that types of observed rupture behavior. PyLith can also be used for volcanic modeling, either with magma chambers or dikes. There's dike inflation and inflation associated with a magma chamber. There's also deformation associated with ruptures. And dike intrusions, you can be related to opening and dilatation. Sometimes we use faults to do that and open the faults up. This is quite different than an earthquake simulation where we're primarily interested in shear deformation associated with faults. This is a diagram that we put together about 10 years ago to describe how PyLith fits into sort of the general workflow of a research problem. So let me bring up a pointer here. Oops. Oh, okay. Click on the pointer, don't try and drag it. So the physics code here is PyLith. PyLith is not a standalone, does everything for your simulation code. In most cases, people start here at the mesh generation step. They may be given a geologic structure. Most people don't go the full procedure of generating the geologic structure using sophisticated modeling packages such as GoCAD or Earth Vision. Usually they have some idea of the fault structure and material properties. So most people start at the mesh generation step. We currently prefer using CUBIT or Trelis. This provides a nice GUI interface. It is available for US federal government agencies as CUBIT and academic institutions both inside and outside the US as Trelis. It has gotten a bit more expensive over the years as Sandia forked off Trelis for a commercial opportunity. We are currently and continue to investigate open source models. TetGen and Gmesh are two alternatives to open source. PyLith does not currently have an interface for ingesting their information. We will continue to investigate those, and hopefully in the long term we'll come up with an open source solution as an alternative to CUBIT and Trelis. Relax does not need mesh generation, so in that case you skip the mesh generation step. There's a GPL code called GeoFest that also does viscoelastic deformation, and there are commercial packages such as Abacus that can do a wide variety of physics implementations. So normally we start with CUBIT and Trelis, generate the mesh, we run our simulations using PyLith, then we want to visualize the results. A lot of quick and dirty, easy visualization is done with Paraview. An alternative Paraview is Visit. Both of those are open source and free. Paraview is probably a little more intuitive to use. In sort of looking at doing more sophisticated processing and analysis of results, we use it generally either MATLAB or Matplotlib with Python, and that provides sort of great for plotting time histories, publication ready plots, doing sophisticated post-processing inversions with those interfaces. For those of you not familiar with Matplotlib, it's essentially a Python module that provides very similar syntax to MATLAB, and Matplotlib is free. It's one of those Python modules, and you have the advantage that you have an entire programming language and additional resources in other modules that allow you to do quite sophisticated data analysis. We generally don't interface with GMT. Relax does, and that's primarily because in PyLith we're mostly interested in visualizing 3D results or time histories, and that's where Paraview and Matplotlib generally provide superior features and visualizations. For PyLith, there's 3 of us that are the primary developers: myself, Charles Williams, and Matt Knepley. And PyLith was forged from the combination of 2 codes: a dynamic modeling code that I developed called EQSim, and a quasi-static modeling code called Tecton that Charles has been involved in since his days in graduate school. And the idea was that those 2 codes were not modern. EQSim was parallel, Tecton was not, but there was a significant overlap in the types of general features that they wanted and related to earthquake faulting, finite element modeling. And so we decided that we would like to model things like the earthquake cycle, and it would be great, instead of duplicating work, to combine those efforts. CIG was forming at the time and offered collaboration with computational scientists so that we could really improve the flexibility, modularity, as well as sophistication of the type analysis that could be done. And so our goal was to develop use modern software engineering to develop an open source community code. And over the past 10 years, we've really stuck to that vision. The governing equations for PyLith currently are the elasticity equation, and a little bit later I'll mention where we are going to actually extend this beyond just elasticity. So written here in index notation, we have the equilibrium for stress. We also have boundary conditions, traction boundary conditions, Dirichlet displacement boundary conditions. On faults, we're going to specify the relative displacement across the fault with respect to some orientation. That's what the R is. And so here's our governing PDE up here in equation 1. In equation 5, we take that PDE, multiply by a weighting function, integrate over a volume, and this is called the weak form, and gives us, we use the finite implementation to take this weak form and solve it. So what we're doing is we're going to minimize the deviation of our solution from the partial differential equation over the volume. So by multiplying by our weighting function, we can select this weighting function to minimize the error in the result. After some algebra, we take equation 5, it ends up looking like equation 6. So we have a term that's related to the stresses and derivatives of our basis function. We have traction boundary conditions, so that integral is over our boundary surface. We have the body forces applied in the volume, as well as an inertial term. So if in the quasi-static modeling, we drop this last term and don't have inertia, that inertia term is what gives us our seismic waves and the propagation of information throughout the domain at relative speeds. In discretizing those volumes, we use what are called finite elements. And here I've shown examples in 2D, where we support both triangular meshes as well as quadrilateral meshes. On the bottom is what people often use in terms of storing the mesh. There's cells. In this case, on the lower left, we have two triangles, 0 and 1. And then we have vertices. And here in this graph, I'm showing how each cell is made up of 3 vertices. Cell 0 is made up of vertices 2, 3, 4. And cell 1 is made up of vertices 3, 4, 5. We use the convention that we number our cells first and then the vertices. Everything has a unique label. We do not number our vertices 0 through, say, n, or in a cell 0 through the same thing. We actually split it up. So whenever we're given an ID, we know whether it is a vertex, cell, or so forth. Prior to PyLith version 2.0, we stored things using just vertices and cells. Beginning in PyLith 2.0, we actually store now the intermediate levels. And this is related to the fact that as we start to do more sophisticated types of analyses, we found it was much more efficient to store this, to take on the overhead of this small amount of information and be able to use more generalized methods to account for the topology of the mesh. And it really has allowed us to sort of clean up the operations that we wanted to do. So there were many times where we needed this intermediate level information. We had to sort of kludge it together on the fly. Now we maintain this as part of the mesh. And especially as we go to sort of higher order discretizations, this overhead is actually much less than it would be otherwise. So here, instead of storing just the vertices and cells, we store the vertices, the edges, and the cells. So in this case, cell 0 is made up of edges 2, 3, and 4. You'll see that they are numbered here in blue, 2, 3, and 4. And each edge is made up of 2 vertices. So edge 2 here is made up of vertex 7 and vertex 8. So similar graph, just an additional layer. When we go to 3D, we have vertices, edges, faces, and cells. Now, after we've discretized our volume or 2D surface into a number of cells, rather than doing, we want to do integrals over those volumes. So we break that into those integrals into a summation over the integrals of each cell. And within for the integrals for each cell, we actually do numerical quadrature, which evaluates those integrals at specific points. And then there is a weighting function for those points. And you account for the difference in the geometry from perfect triangles and perfect squares. This is the essence of the finite element method. And so our previous equation becomes a summation over all of the cells, summation over the quadrature points of our stress function, derivative of the basis function times the weight times the determinant that corresponds to this mapping of reference to our actual cell. And so all of our integrals become summations. In actual code, these are just for loops that involve summations. And we account for which these basis functions, which vertices are associated with that cell. So we have global degrees of freedom, and we end up with large matrix equations. So we end up with, we can form our equation in this form where we have a matrix A times a vector U equals a vector B. In our case, this matrix A is usually in quasi-static cases, essentially the stiffness matrix. And then the B vector is what we would call our force vector, which is related to our tractions on our boundary, as well as the body forces integrated over the volume, and we solve for U. So this is sort of the classical linear equation that can be solved in a variety of ways. PyLith uses PETSI, which is a large parallel library for solving matrix equations that provides various ways to do this. You can do the general sort of exact solutions through what's called LU. There are also a number of iterative methods, additive Schwartz, conjugate gradient, and so forth. And PETSI allows you to switch on the command line between these, that it really allows you to pick the best solution scheme for your problem. I see we have someone raise their hand, so can you either, if you have a quick question, can you type it in the chat window? An equation, U of t, in this case, is displacement. In the case that we have a fault, PyLith implements a fault in a very specific way. It is generally an interface in the interior of a body, and we couple the deformation across that through continuity of the tractions across that interface. So here I have drawn a conceptual volume shown by the black line, and then within that volume I have a fault interface, and I put a normal on the interface. It's arbitrary which direction I pick. PyLith picks, it's somewhat arbitrary, but once we've created the mesh, we have a definitive way to define what the normal is. We'll have relative displacements U across the interface, as well as tractions on either side. We take the convention that the normal points to what we call the positive side of the fault from the negative side of the fault. So that's why we have pluses and minuses to distinguish the positive and negative side of the fault. This is what it looks like within the code. So if originally we have a mesh here, I have two strips of triangles, and I want to create a fault running down the middle, and I want that fault to end here at this vertex. The first thing we do is we split open the fault and we add additional vertices. So originally we had the vertex in blue. We add a vertex on the positive side of the fault. So in this case, my normal is pointing to the right. And then we'll replace the edges on the right side with those new vertices. Notice that down here at the edge of the fault, I did not add a new vertex. So this is going to force the fault to be closed or sort of disappear at that end. This is new in PyLith 2.1 to be able to handle these, what we call these buried edges at the interface. At the other end, you'll notice that the end of the fault does not have, still has the two vertices, so that allows slip to still occur at the free surface, but to buried edges, the slip is forced to be 0. The next step, once we add those new vertices, is to update the connectivity arrays on each side of the fault. So the cells on the positive side of the fault are, instead of having the original vertices, they have the new vertices shown in red. So we identify who those cells are because they're on the positive side of the fault, connected to the fault, have an edge on the fault. And so we update those. Then we need to update the surrounding the surrounding cells that may not have a face or an edge on the fault, but may just touch a single vertex on the fault. So that's what I show on the far right. So in the end, what we have is we have split the mesh, we have additional vertices, and these edges connecting the two vertices are associated with Lagrange multipliers that allow us to specify constraints on the tractions and displacements across the fault. In mathematical form, we have, here's our normal Neumann boundary condition with tractions on the exterior boundaries. Our faults, traction continuities look very similar. Here, instead of a t, this is a lowercase l corresponding to a Lagrange multiplier. So our Lagrange multiplier is equal and opposite tractions on the two sides of the fault. And so it looks very similar. Notice that on the positive side of the fault, we have a negative sign out in front. On the negative side of the fault, we have a positive sign. This is related to the fact that these are internal interfaces and those tractions are equal and opposite. Our constraint on our relative displacement across the fault, if we want to specify a slip, this is a given supplied field. You could think of it as a Dirichlet boundary condition, except in specifying slip, it's a relative displacement. So here's our solution points in terms of our global degree. We're generally solving for the displacement field, so we don't know what these displacements are. We want them to be constrained such that the relative displacement across the fault matches our prescribed slip. So our constraint equation is shown here. Please continue to type in your question, and I'll continue to move on and come back. Here is the system with cohesive cells. So originally we had just A equals B. Our fault constraints is supplied in terms of constraints on the displacement. Constraint matrix C times U. C holds all of the relative orientations between the two sides of the fault and which degrees of freedom are involved in the fault. D is our slip. And so we take our original equation A equals B and CU equals D and form a matrix equation that now is A, C transpose, C 0, that matrix times U, the Lagrange multipliers equals B and D. So the question was, where do the plus and minus come in? That comes back in here from our definition of the fault, where the normal is pointing. We have to describe one side of the fault relative to the other. And so the normal, when we form the fault, points from what we call the negative side of the fault to the positive side of the fault. And so when we pull the two sides of the faults, we will, given a single a list of the vertices on the fault, we will sort of arbitrarily form which side the normal points to. And then once we've picked that normal direction, the original vertices become the negative side of the fault, the new vertices become the positive side of the fault. So going back to our equations, in prescribing slip, we specify D, that's on the right-hand side, and solve for the Lagrange multipliers and displacements. If we have a fault friction or dynamic spontaneous slip, then D is unknown. Generally, the tractions are constrained. And in the current implementation, we adjust the fault slip to be compatible with the fault constitutive model. We do have a new formulation that we're in the process of implementing that redefines the Lagrange multiplier and moves it to the right-hand side, essentially, and allows us to solve this more efficiently. The advantages of using this approach with the Lagrange multipliers is the fault implementation is completely local to a cohesive cell. The rest of the volume does not need to know anything about that a fault exists. The solution includes the tractions generating the slip. That is the Lagrange multiplier. It retains the block structure of the matrix, including symmetry, and the offsets in the mesh mimic slip on natural faults. So instead of creating a very highly localized strain region, such as you might do if you didn't include Lagrange, didn't split the fault, we actually have much better accurate representations of the shearing when you have an actual dislocation in the mesh. The disadvantage is that the cohesive cells require adjusting the topology of the finite mesh. That's all done for you when you use PyLith. And our development of a scalable solver is more complex, but we have also taken a lot of the work out for you and developed a scalable preconditioner solver that is specific to this type of problem, and it works quite well for meshes with millions of degrees of freedom. So we'll start to now move into describing how you run PyLith and the features of PyLith. So generally, the workflow is you generate your mesh. In very, very simple cases, you can use a text editor to generate your mesh. We primarily use that for test cases that are just no more than a few cells. Anything more than just a few cells, we use CUBIT and Trelis. From CUBIT and Trelis, you'll export an Exodus file. This is a binary. It is a netcdf file. And you can look at these files in Paraview to see what your mesh looks like. From Lagrange, you have to export both GMV and pset files. In addition to these, the mesh itself, you need the parameters. We often generate these using just a simple text editor. We like Emacs. It's a great sophisticated text editor. It has a bunch of modes for editing different types of files. The simulation parameters are generally captured by both a parameter file. We use the extension .cfg. These are simple files that where we assign parameters values. In some cases, these are actual objects or arrays or strings, numerical values, integers, floats, and so forth. From the .cfg file specifies all of the parameters in terms of objects and values. When we want to specify for our boundary conditions or material properties, those generally need a more sophisticated specification. We use what are called spatial databases. These are generally just text files, but they can be very large databases, such as a seismic velocity model. That can be gigabytes in size. We have a single interface that is used to access those. It generally is just doing queries in a volume for values at a point. That's why we call them spatial databases. For a text editor, we can do things like single values, values along a line. We'll often generate spatial variations of slip or more sophisticated variations in parameters using either generally we use Python scripts, or you can use a MATLAB script as well. So when you run PyLith, you're generally going to get an Exodus file, a .cfg file, as well as one or more spatial databases. When you run PyLith, you'll generate, depending on which type of output you select, VTK files, which are ASCII files, or HDF5 files. HDF5 are our preferred files because they allow easy access to the data themselves from Python or MATLAB for post-processing. They're binary. We can write them in parallel, so they're much faster output. The disadvantage is that you can't look at the file directly because it is binary. So if you're doing just a very simple problem, it's often easier to start with VTK files because you can look and you can see what the VTK file looks like. So Spatial databases, examples, a uniform value for a Dirichlet boundary condition. That's what we call 0D, so that's a point value because it's uniform. If we have a piecewise linear variation for, say, a norm on boundary condition, then we have points along a line. We refer to that to a 1D variation. If we have a variation over a surface, that would be 2D. And if we have a volume, such as the Southern California Earthquake Center community velocity model, we have an interface to an older version of that seismic velocity model. That's a 3D specification. And for that particular model, there's a very specific spatial database for accessing it. Generally, the spatial databases are independent of the discretization. So whether you're using triangular cells or quadrilateral cells, you can even switch the mesh, switch the resolution, but you're generally going to keep the spatial databases. So that's really trying to set your boundary conditions up based on what problem you're trying to solve rather than how you're trying to solve it. So available spatial databases, these are the object types within PyLith. Uniform database is optimized for a uniform value. You can specify the parameters right in the .cfg file. A simple database, these are simple ASCII files for 0D, 1D, 2D, or 3D. We have the SCET Community Velocity Model version 5.3. And then we have a special case of a uniform database when we want zero displacement boundary conditions. We use this often enough that rather than specifying 0, all you do is have to specify that you want to use that database, and it automatically supplies 0 values for whatever degrees of freedom you specify to be constrained. So let's go over the list of features in PyLith 2.1. We have time integration schemes and elasticity formulations for quasi-static problems for both infinitesimal and small strains. And I'll point out that currently version 2.0 and 2.1 have a bug related to small strains, and that's one of the things we're in the middle of fixing. For explicit problems, we have both infinitesimal and small strain formulations. We also have numerical damping via artificial viscosity. This helps stamp out very high frequency oscillations that often show up in dynamic problems. We have a variety of bulk constitutive models, all in 2D and 3D. We have your generic linear elastic model, a linear Maxwell viscoelastic model, a generalized Maxwell viscoelastic model that you can take that generalized Maxwell model and make it into a Berger's body, as well as some other viscoelastic models based on the selection of the parameters. We have a power law viscoelastic model and a Drucker-Prager elastoplastic model. And for the Drucker-Prager, you can specify whether your yield surface conforms to the von Neusiedl model and sort of the circumscribed, inscribed, and sort of how your yield surface matches some of the parameters. For boundary and interface conditions, we have time-dependent Dirichlet and Neumann boundary conditions. Those are Neumann refers to the traction boundary conditions. Dirichlet refers to constrained displacements. Absorbent boundary conditions for dynamic problems. We prescribe slip and fault interfaces with multiple ruptures, so you can have a single fault rupturing or multiple faults. Then you can have a specified interseismic period and then additional ruptures. For fault interfaces or dynamic fault interfaces, that refers to fault friction, where you specify a constitutive fault friction model, and the fault will slip according to that fault friction. We now, with 2.1, offer fault interfaces can have T-intersections. So you'll have, if two faults intersect, generally you need to describe one as being sort of the through-going fault, and then which fault intersects it and dies out, essentially. We also have time-dependent point forces and gravitational body forces. For fault constitutive models, we have static friction, linear slip weakening, linear time weakening, and Dietrich-Karina rate and state friction with the aging law. For sort of time stepping, we have automatic and user-controlled time stepping. You can specify initial stresses and strains. You can import the mesh from, as I mentioned before, Lagrange, CUBIT or Trelis, and simple ASCII files. We have output via VTK and HDF5 that includes the solution over the volume, the solution over a surface boundary, the solution interpolated to user-specified points, such as GPS or seismic stations, and you can now include the station names. You can output state variables such as stress or strain for each material, and you can output the fault information, that is the slip or tractions on the fault surface. Additional features of PyLith: automatic conversion of units for all parameters. So almost every parameter that has units, you specify the units. If you don't specify units, it's assumed to be SI units. That's meters, seconds, and pascals. Question on what is the viscosity range that PyLith can compute. PyLith can really handle any range in terms of viscosities and Maxwell times. There are, in terms of handling units, everything within PyLith is done non-dimensionally. So based on the non-dimensional parameters, you can sort of select anything from length scales to time scales. And so if you have a very sort of low viscosity, your time scales are going to be much shorter than if you have a very high viscosity and longer Maxwell time. We offer parallel uniform global refinement. In that case, what happens is if you need to run at a very high resolution, you can have, after distribution of the mesh, which PyLith does for you, you can have the mesh refined. And when it refines, that increases the resolution by a factor of 2. You can have multiple refinements. The mesh does tend to get a little distorted as you refine it. But that allows you to run much larger problems than what you could otherwise if you had to generate your actual mesh within CUBIT. We have PETSI linear and nonlinear solvers, and one of the relatively new features is output of the simulation progress. It shows the timestamp, shows how far the simulation has proceeded, and an estimated time of when the simulation will finish. So those are all the features that are in PyLith currently. We are constantly working to add new features. Right now, we're taking another big step in PyLith capabilities. We have a new fault implementation that we worked out all the theoretical steps involved in terms of how to formulate it for spontaneous rupture, and so we're working on its implementation. We're working on support for higher order basis function. This allows you, instead of generally providing just linear basis functions, which means that the stresses are about as most as you can get is linear within a cell. For triangles and tetrahedra, it's constant within a cell. So if you want to handle sort of higher resolution variations and stresses, you need to go to higher order. So we're working on support for that. It'll also allow us to get higher resolution for a given mesh. Adaptive time stepping, preparing for multi-physics. So we're doing some reformulating of actually how we do the finite element integrals to prepare for multi-physics that would allow you to couple elasticity, fluid flow, heat flow, and solve poroelastic problems and other similar types of problems. Really, and it also in that same step, it would allow you to add in additional bulk constitutive models. Whereas right now, sort of the physics, we have some elastic bulk constitutive models, and they're sort of separated from the actual equation. So we'll have greater flexibility for the types of physics that we can do, as well as the discretizations. And we're with that, the PETSI group has working on how to scale to more cores in terms of loading up the mesh. So short-term priorities are the multi-physics, and with that, a multi-grid nonlinear solver that the PETSI group has been working on. We still have high on our priority list multi-cycle earthquake modeling, and we'll get a big step towards that as the adaptive time stepping that will allow us to really have the variation in time step corresponding to the physics, so that if you really don't need a small time step, larger time steps can be taken. And so the release schedule right now is we'll have our bug fix release hopefully in the next month related to finite strain and restarting simulations with viscoelastic materials. And so Paul had a question related to restarting. As we, with our new formulation, sort of with the, in sort of immediate priorities, we can, with the adaptive time stepping and so forth, we think we'll have sort of a better way to restart, more sophisticated. Right now, you can do a restart. Restarting for viscoelastic materials, we found there's a small bug, so we'll be fixing that in the next month. And so right now, you can, with a viscoelastic formulation, do a complete restart from a previous time step that has been saved. And that works great for prescribed slip problems. Right now, what's missing is if you want the fault friction. It's a little kludgy to get that. Bug fixes will also be looking at the better example for gravitational body forces. That's a work in progress. So that'll be our bonus tutorial session in about a month. We're looking at hopefully by AGU having version 3 out with the new fault implementation, support for higher order Betas functions, and adaptive time stepping, and sort of a rewrite of how we do the integration, so that next summer we can release our first multi-physics version with support for incompressible elasticity, as well as heat and fluid flow coupled to elastic deformation. Before I run an example, I want to go sort of a brief outline of how the code is actually put together. PyLith is designed to be flexible and modular, so most features are confined to a small set of objects. It is designed so users can be able to add new features or extend the code in certain ways, primarily boundary conditions, bulk constitutive models, and fault constitutive models. We have designed the input and output to be user-friendly. For example, directly interfacing with the meshers, so you don't have to do any post-processing of those files as input and output that can be read directly into things like Paraview, or read the arrays directly into MATLAB, or viewed in Python for additional post-processing. The top-level code is written in Python, which is very expressive, doesn't require many lines of code to do sophisticated things. It also supports dynamic typing, so you don't actually have to, on the fly, it'll determine whether things an object or an integer or string or a floating point number. And this is what allows it to be able to handle a user's extending the code, because you can just sort of say, hey, it's an object, and it'll load it up at runtime. The low-level code is written in C and C++, C for all of PETC, and C++ for the main Python code. I mean, not the main Python code, the main PyLith code. The C++ and Python are object-oriented, so we have generally a direct mapping from an object in Python to an object in C++ that keeps things modular and fast in the C++. This is what the dependencies look like. So PyLith sits there at the top. That's our Geodynamics code. It makes use of spatial data, which knows nothing about physics. It just knows about how to store things, basically storing values at points with some sort of topology. PETC is our linear algebra parallel data structures. That is provided by Aagaard National Lab. We maintain spatial data, and then our basis functions currently are being handled by a package called Fiat. At a lower level, we have a number of other low-level sort of packages for netcdf and hdf5 for storing there are large binary files, netcdf for the meshes, hdf5 for our output. Proj4 is a library for doing geographic projections. So we support geographic projections and converting from one projection to another. So you can specify your boundary conditions in one projection and your mesh in another projection, and all those transformations will be handled automatically. Pyr is what we use to gather all of the user input and do some basic checking and monitoring. NumPy is a Python module for arrays. And at the very low level, we have MPI for parallel processing and BLAS and LAPACK for matrix manipulation from PETSI. This is the main application flow. So at the very top level, we have an object called PyLith app. That's our main application. It has a function main that looks not much more complicated than what is shown here. It basically create the mesh, initialize the problem, and then run the problem. We have two types of problems currently, a time-dependent problem and a Green's function problem. For the time-dependent problem, it really boils down to initialize the formulation of the equations, and then while t is less than the end time, get the time step, advance the time step, or advance time by that time step, and then do a post step. So in the pre-step, that's set our boundary conditions. Step, we solve the equations. Post step, we write output. So one of those formulations, if we have an implicit formulation, that's for the quasi-static problems. It has functions initialize. Pre-step, it sets the values of the constraints. In the step function, it computes the residuals, solves for the increment in displacements, and then in the post step, we update the displacement field with that displacement increment and write output. And so that's sort of at the very top level, that's what PyLith looks like, and these are that's all written in Python. We have, for a number of components, they have both a Python object as well as a C++ object in order to communicate information back and forth and access the C++ from Python. We use a package called Swig that generates these interfaces on the fly at build time. And so the user will generally interact with what are known as properties and facilities. The facilities, they're also known as components. So properties are things like strings, floats, integers. Facilities are basically other components. The Swig and C++ are optional. For low-level things, we have the C++. For very, very high-level things, we may not have those because there's no need to have the computational engine part. So things that are just like a PyLith app does not have a C++ part because all the computation is done via other objects. So this is what the hierarchy looks like. So you can think of the PyLith application as a hierarchy of all of these components. Components often have subcomponents. Those subcomponents have their own subcomponents. But each of those, in addition to subcomponents, they can also have properties, which are the strings, floats, integers. And so our top application, it doesn't have any properties, but it does have facilities as a mesh generator or problem, and then an interface to PETSI. A time-dependent problem, it has a property for the dimension of the problem, whether it's 2D or 3D. We no longer support 1D since we can't do any real physics in 1D. Facilities as a normalizer for the non-dimensionalization, materials for the different material properties, BC for boundary conditions, interfaces for the faults, gravity field for gravitational body forces, and the formulation for whether it's an implicit or explicit time stepping. Another example is our prescribed slip, also known as fault cohesive kin for our object. It has properties. It has an ID, a name, an up direction, normal direction. And then its facilities, it has quadrature, earthquake sources, and output. An example of an earthquake source is our prescribed kinematic source that has its property is the origin time. And so that is the origin time in the simulation, and then a slip function that specifies the temporal variation of slip and the spatial variation of slip. So you can get an idea of how each component can have both just sort of simple properties as well as more sophisticated subcomponents to handle various aspects. So here's a very simple toy problem. I believe this is step 01 in 3D examples hex 8. So we have roller boundary conditions on the bottom of the domain. We're going to apply both axial or shearing as well as sort of axial compression via Dirichlet boundary condition. This looks like a simple problem with just a few boundary conditions. As a hierarchy of components, this is what it looks like. A lot of these don't have to be specified. There's defaults for these, but you can see that as you walk down from the main Pyth application up here on the left, for our mesh generator, we have the mesh importer, we have the type of reader where it's getting the mesh. So from CUBIT, to just change to an ASCII input, you would just change that one component over there on the upper right. For our time-dependent problem, we have our non-dimensionalizer. We have both a quasi-static and dynamic non-dimensionalizer just to make it easier to specify those different non-dimensional parameters. We have boundary conditions. We name our boundary conditions. In this case, we have 3 Dirichlet boundary conditions. Each of those are specifying the boundary conditions using spatial databases, so they each have their own simple database subcomponents. For our materials over here on the left side, we have a lower crust as well as an upper crust material. So each of those have special objects. We have outputs for each of those that specify how often we're going to want stress and strain output as well as what those parameters are. So you can see that, as you break it down, it actually turns out to be quite simple, but it is really a hierarchy of components. And in our parameter file, we really make use of this hierarchy of components to specify the parameters. I'm going to skip over the testing. You can come back and read this at your leisure. In terms of running problems, one of the first problems you're going to be faced with is whether do I want a hex mesh or a tet mesh in 3D or quads or triangles in 2D. Hexes and quads are slightly more accurate and faster because they have a few more degrees of freedom per cell. However, tetrahedron triangles handle complex geometry much better, so there are some cases where you cannot even generate a mesh using hexes and you need tets, and so that right away will dictate which type of cell you use. CUBIT has support for complex variation in the material of the discretization size with quads, and so that helps it sort of stand out from some other mesh generators. So it's easy to vary the discretization size with triangles and quads. There's no easy answer for a given accuracy. A finer resolution tet mesh that varies in the discretization size in a more optimal way might run faster than a hex mesh. So it really depends on the problem. You generally want to sort of start with something, start at a coarse resolution, and then get finer as you need to. Our best suggestion is to check and double check your mesh. Were there any errors when running the mesher? Are all the boundary conditions marked correctly? And you want to check your mesh quality. If you don't have a good quality, then your solution may not converge. So Stephanie will answer your question in a couple minutes. Sorry if I missed it earlier. CUBIT Workflow, you generally create your geometry. That may be surfaces from points, curves, or other basic shapes, or subdividing surfaces, chopping blocks with other blocks to create your geometry. You create your final mesh by specifying the meshing scheme. That's whether it's a triangle, a tetrahedral, quadrilateral, or hex mesh. You specify how the mesh size varies. You generate your mesh. You smooth it to fix any poor quality cells. And once you have the mesh that you want, you create your node sets and blocks. Node sets are for boundary conditions and blocks are for materials. An additional thing that is needed now when you're using buried faults is to create a node set for those buried fault edges. And finally, you export your mesh using the Exodus 2 format. Some of the issues to be aware of, if you have topography and bathymetry and want to include it, our best suggestion is to first ignore it, make things flat, make a simple shape, unless you know it matters. If you do want to include it, we have some examples that show various ways. For a rectilinear grid, you create a UV net surface. For triangular facets, you want to create a UV net surface on that surface. So basically, you convert a triangular surface, create a rectilinear representation of that using a UV net surface, and then you use that actual UV net surface in your map mesh. Examples, meshing is where you'll find examples for those. Fault surfaces, build the surfaces from contours is usually easiest. Include features at the resolution that matters. Even if a geologist provides you a fault surface, sort of a surface trace at the meter level, you probably don't have enough other information at the meter level, and it may not matter if your observations, such as GPS stations, are kilometers apart. In terms of performance and meshing, there are a number of points in your splines and curves has a huge effect on mesh generation runtime, so that's why you want to start simple and then work your way up. CUBIT Trelis do not run in parallel, so you're limited to using a single processor / core. So even if you have a workstation that has lots of cores, generally CUBIT and Trelis don't know how to take advantage of that. And you can use uniform global refinement in PyLith to generate meshes that have more than 10 million cells, even 100 million cells. I think I'll skip over these mesh generation best practices. You can come back and look at those at your leisure. Generally, for modeling tips, start in 2D, then go to 3D, start at coarse resolution, and then go to finer resolution when you need it. And always use your intuition and analogous solutions to check your results. PyLith is very good at spitting out a solution, but in many cases, if you deviate, there may be a difference from what you think you asked PyLith to do compared to what you actually asked PyLith to do. So this is normally the case of boundary conditions. So you should check to make sure that your boundary conditions look correct and or you're specifying the fault slip in the way you think you're specifying fault slip, so that when you look in your results, you actually get the results that you want. Do not ignore error messages and warnings. We'll come back and discuss a number of these things tomorrow in our afternoon session. Remember the email list and the PyLith user resources. You can look at those links at your leisure. We'll discuss PyLith info in detail tomorrow, as well as diagnosing error messages. So work through the examples. That's chapter 7 of the manual. Here's where the source files are if you have the binary. And as you progress to trying to run a research problem, our best suggestion is to modify an example that looks like a problem of your interest. So before I run an example, I'm going to answer Stephanie's question of what was the difference between Lagrange multiplier approach and traction at split nodes. Generally, the fault implementation in PyLith is quite similar to other traction at split load techniques. It's really in the bookkeeping and our definition of what the Lagrange multiplier is and how that is used in formulating the equations that are solved. The PyLith paper that was published in JGR in 2013 describes in detail our fault implementation approach and some of the trade-offs, and as well as a comparison with results from PyLith and other codes for dynamic rupture examples. Are there any immediate pressing questions before we go on and run an example? Okay, so we'll stop sharing the document and I'll share my